Hello everyone, I would like to welcome you all for today's class. We will briefly look at what we did last time about the allyl silane based chemistry. We looked at various aspects of allyl silane based reactions which involve inter as well as intramolecular reactions. One of the first things that we talked in principle was that the formation of the beta carbocation with respect to silicon is stabilized, and therefore wherever there is a possibility the formation of the beta carbocation is preferred. One of the things that we discussed was of course the Diels-Order reaction of this kind here, that we took this type of diene containing silicon moiety and then reacted with this dienophile. And what we saw was of course formation of this kind of product with endoselectivity. That means the stereochemistry of this carbon silicon bond was the same as the stereochemistry of this electron withdrawing group here of the dienophile. That means if this is alpha, so this is also alpha. And then when we reacted it with an electrophile like a proton or any other electrophile, then of course the double bond interacts with the electrophile in such a fashion that the carbon electrophile bond formation occurs here to give this particular type of carbon E bond, and of course the cation is coming at the beta position with respect to silicon, and again emphasizing on the fact that there is a beta silicon effect. So the regioselectivity of the double bond interacting with the electrophile was basically guided by the beta silicon effect. Now since this carbon silicon bond is alpha oriented, therefore the carbon electrophile bond becomes beta oriented to avoid the steric interaction. Of course this kind of endoselectivity of this type is basically governed by the Diels-Order reactions rules. Then we also looked at the pyrrole palladium complex based chemistry, in which we took an example of this kind, in which there is an allyl acetate moiety and allyl silane moiety embedded along with a alpha beta unsaturated ester moiety. Now when palladium 0 was reacted with this, we saw the formation of this bicyclic molecule. Of course in this context we discussed in detail how this allyl acetate and allyl silane containing compound forms a kind of 1,3 dipole, which is basically guided by the formation of pyrrole palladium complex, and of course the leaving group that comes out from here cleaves the carbon silicon bond to make an anion here, and such a dipole then interacts with the alpha beta unsaturated system to allow a 2+3 cycloaddition to form this kind of cyclopentane molecule. Finally, we also looked at the intramolecular cyclization of an allyl silane under basic conditions, in which tetrabutyl ammonium fluoride was taken as a nucleophile which interacts with the silicon, making a silicon fluorine strong bond and generating an anion here, which then allows cyclization in this particular fashion to occur. Here the driving force is of course the formation of a strong silicon fluorine bond. So these are the things we discussed, which is basically governing the allyl silane based chemistry. Now we look at it now what is the vinyl silane based chemistry. Now a vinyl silane based chemistry is very similar in terms of the possibility of reacting with electrophile, follows the same principle that we have been talking about it. Now if we see this vinyl silane, to be written like this, then when an electrophile reacts, the electrophile could be expected to react either at this end of the double bond or can be expected to react at this end of the double bond. Now if we compare it with what we did it last time with the allyl silane based chemistry, we all the time said that electrophile attaches to this carbon atom at the end, so that the cation forms at the inner carbon atom, so that is basically beta to the silicon. So in this case, if the electrophile attaches towards the end, then you generate a cation which is alpha to the silicon, which is not stabilized. But if it attaches onto the same carbon, that means the electrophile attaches to the alpha carbon which holds the silicon group, then we generate a positive charge on the beta carbon atom, and therefore it can be stabilized due to the same kind of overlap as we have discussed, that the sigma bond overlaps with the p orbital, which is an empty p orbital. It is kind of hyperconjugation as we have discussed last time. So it is very similar to the stabilization of beta carbocation that we saw in the case of allyl silane. The only difference is that the electrophile attaches to the same carbon that holds the silicon group. So now if you look at it very carefully, this intermediate here, and react it with an electrophile such as acetyl chloride in the presence of aluminum chloride, which is expected to give an intermediate of this type, which is a very reactive intermediate. So we will have AlCl4 minus here, and this can then react with the vinyl silane. As we discussed, the vinyl silane reacts in such a way that the electrophile attaches to the same carbon that holds the silicon. So obviously we will get the attachment of the electrophile here, and the carbocation comes here, which is nothing but a beta carbocation. Then of course the silicon breaks off with the from here with, say for example, when the nucleophile such as Cl minus takes the silicon from here, and you get the product as shown it here. In a similar fashion, if we take the other vinyl silane of this kind, which is different from the top one, and we expect that the attachment of the electrophile occurs onto the same carbon as this silicon holding carbon, and therefore we can get the product such is like this. Now it is quite possible that the if we try to rationalize it, then vinyl silane additions proceed with retention of double bond configuration and follow a similar principle as that of allyl silane addition. What does it mean? It means that, say for example, if you have a vinyl silane like this, so the addition of the electrophile, if it takes place from top or bottom face of the double bond, the silyl moiety, like for example if you have this double bond with the silyl group here, now silyl group here and A are trans to each other, the silyl group and B are cis to each other. So if the electrophile, say for example, attaches to the same carbon that holds the silicon, so that the beta carbocation is formed, and if it attacks from the bottom side, for example here, which we expect this intermediate to form, and that will undergo slight rotation here in such a fashion that the silicon then will have an overlap. That means the carbon silicon sigma bond will have an overlap with the empty p orbital here, and then of course we will get the double bond. But in this case, as you can see, there is a retention of double bond. That means the silicon and the electrophile occupy the same position in the double bond. So the principle of least motion suggests that the electrophile moves into a position close to that formerly occupied by the silyl group. This is what is the formal rule that says that there is a retention of double bond configuration. And now if we take some examples where we can see such things happening is for example, if we take this where the R1 group and the silicon are trans to each other, then of course we also get the R1 and the electrophile coming also in a trans fashion. So now if we take a double bond like this where silicon and the phenyl group are trans to each other, we add deuterium chloride to it and we expect that the deuterium chloride for example attacks from the top side and if we write with the orbitals being like this, then if the deuterium attacks from the top, then we get to see such a carbocation intermediate and this carbocation intermediate now will undergo a rotation here in such a fashion that the carbon silicon bond goes down. That is the least motion that we can expect to see in this case, that is what is energetically favorable and it goes down, and if that happens then deuterium comes into this position and now your nucleophile attacks, you have a beta carbocation, the carbon silicon bond breaks with the help of the nucleophile and of course this bond breaks and we get this product in which the deuterium is now occupying the same position as the silicon. So we have to make sure that the carbon silicon bond lies in the plane of the p orbital, that is why we have rotated it in this fashion. So stereospecificity is attributed to a bridging interaction between the silicon atom and the 2pz orbital of the adjacent carbocation as shown it here. So this is how the vinyl silanes react and we get the product in which the silicon group gets replaced by the electrophile. Now we have very interesting examples of what is known as Nazaro cyclization or dienone cyclization. In these cases the regioselectivity is very important. Now what is Nazaro cyclization or a dienone cyclization? As you can see it here, if we have a dienone which is conjugated, this is mean there is a diene and of course there is a ketone which is conjugated, and when this undergoes cyclization in the presence of an acid, could be a protic acid or a Lewis acid, then one can expect to get a product of this kind here. So basically what is happening is something of this sort happens and then you get an intermediate of this kind here like this and get a positive charge here, and of course you then get the enone by the loss of this proton here. So this is what is called as a Nazarov cyclization or dienone cyclization. So how do you make this dienone? You can react the acyl chloride with vinyl silane. So as we discussed that the vinyl silane react with an electrophile. In this case the electrophile is going to be this particular positively charged species, and you have here SnCl4. So we write here the nucleophile being this is the electrophile that is going to be there, and of course the vinyl silane reacts and the carbon silicon bond is replaced by the electrophile, and that is what is happening. So this carbon gets attached to the this electrophilic part and we get this intermediate. Now this intermediate is not a symmetrical intermediate as we have seen it here. This is a symmetrical molecule, therefore it does not matter whether double bond comes in this direction or double bond comes in this direction. But this is not a symmetrical dienone, and therefore when this is treated with continues to be treated with SnCl4, then of course SnCl4 will react to the oxygen here and you have an electrophilic oxygen and then double bond here. Now what can happen, there are two possibilities that can happen to this intermediate. Either you get the movement of the double bond being in this way, so that gives product of this kind here, let us put M here and a positive charge being here, and then this loses a proton, then of course we get a product of this type. Now this is what is seen, and it is not seen the other way around, or the major product is this. The other possibility is that this intermediate also we can write it in this fashion, where the electrophile can react in this fashion here, Cl4 minus and positive charge here, and now double bond could move in this way, that, and of course we can expect the product formation to be like this. OM if we say, then we have a positive charge being here, and that leads to the formation of double bond being here. So this product is different and this product is different, but this product is having a double bond which is more substituted, and therefore this is thermodynamically more stable, and that is the reason why this particular product has formed. In a similar fashion, if we try and take the molecule like this, in which now we see that what we have is an inbuilt silicon vinyl silane into the dienone. So as one can expect that when the proton reacts with it, the protonation occurs it here, and then you get a positive charge on the oxygen. Now this particular positive charge can allow the double bond to move in this fashion, as one would expect, that allows the formation of the positive charge. Once the double bond moves, then you get this particular intermediate. Now this is a beta and this is the alpha, and now this neutralization of the positive charge occurs, and you get this as the exclusive product. What is the other possibility? The other possibility, as we can anticipate but it does not happen, is that once this species is formed, it can undergo cyclization in this fashion, and then what generates is SiR3, and you generate an OH here and a positive charge here. Now in both the cases, here the positive charge is stabilized as an allyl cation as well as by the silicon beta effect, but in this particular case it is only allyl, and of course it is a tertiary. In this case it is secondary, but then silicon positive effect, beta stabilization of the cation at the beta position by carbon silicon bond is more important, and therefore you get this particular intermediate, and not this does not form this intermediate what we would expect it to form. So which is very different from what we saw in the previous case. Now there are some other examples in which the beta effect of the silicon can be seen, and that involves like a protonation of an imine also, like this here, and this protonation can occur at this position here, and what it happens is it allows the intermediate to form in such a way that one can write down the conformation of this particular intermediate, and we can say that, say you have a silicon here, and you have a possibility of positively charged iminium ion to be written like this, and of course you have a pH here like this, and then what happens is, of course, you can allow the reaction of the vinyl silane. Now you have 1, 2, 3, 4 and of course 5 here, and this is the 6th carbon where the attack takes place, and that leads to the formation of the product than one would expect, and that product we can write it in this way. Now we have here phenyl and of course you have a hydrogen here, and then you have cation which is beta to the here. So this is the place where the cation is formed. The nucleophilic reaction takes place onto the carbon where the silicon is attached, and therefore this hydrogen of course is pointing upward, and therefore this is the beta configuration. Phenyl is anyway pointing upward, so it is beta configuration. So this is how the product forms. So now what we have the next is the coupling reaction of this type of intermediate. Another example in which you can see that you have a vinylsilane, and when this is treated with the formaldehyde in the presence of camphor sulfonic acid, which is a protic acid and which looks like this. This is the camphor sulfonic acid, and this is a good acid to protonate the formaldehyde. And how the reaction occurs is that you have here the NH which is now having a lone pair of electron, and then you have a methyl group here, then you have an OH group here, and here you have silicon, and let us say you have R3, and whatever the group is attached to here we write it as R say 1 here. So 3 groups are attached to silicon, and this now this reacts with formaldehyde, and formaldehyde reacts in the presence of H plus, and the nucleophile of the nitrogen attaches to the carbon atom, forming an intermediate of this kind here, and then you can expect that silicon is here and you have the substituent R1 here. Now in this case here is methyl group. I will write it again, and methyl group here. Now this again under the protic condition loses the proton, the OH group upon protonation, and that forms the intermediate of this kind here, and then what you have is a silicon which then reacts in a similar fashion as we have discussed earlier. R3 is this reacts in this way, and positive charge is saturated, and here of course we have methyl and the OH here, and that cyclization allows the formation of the product to take place in this fashion. So once the carbon bond is formed, the double bond forms through the beta carbocation. Now this kind of beta carbocation effect is also not every time successful. Sometimes it can be overridden because it is a relatively weak effect. For example, if you take a substrate of this kind where we expect that the carbon atom that holds the silicon attaches to the electrophile in the presence of a Lewis acid, then one can expect something like this to happen. Say if you have a MXN as a Lewis acid. But then as you can see here that you have formed a primary cation, although it is beta to the silicon, but it is a primary cation, and therefore formation of this after the loss of carbon silicon bond does not happen. What happens actually is that once the Lewis acid like aluminum chloride reacts with it, then the beta position, that is not the carbon holding silicon but the next carbon, attach it in this fashion here, in this way, forming a 6 member ring, that is 1, 2, 3, 4, 5 and 6 member ring, and now it is an alpha carbocation next to the silicon, but which we now say that it is not stable, and therefore since it is not stable, it immediately undergoes a 1,2 hydride shift and forms a tertiary cation here. Now this tertiary cation, as you can see, is not only tertiary cation but is also now beta. This is alpha and this is beta. Here it is beta to the carbon silicon bond, and therefore now it has a double stabilization, and then now the loss of silicon carbon bond occurs and this product is formed. So, this is a very interesting example where the beta effect of the silicon can be overridden. So, we will stop it at this stage and take up the remaining part of the silicon based chemistry next time. Till then you can read more aspects of the vinylsilane based chemistry, and we will discuss about it in the next class. Thank you and take care. Bye.